Okay, let's conclude the chapter with just some final thoughts. This is just one short podcast. The author himself, Peter Webster, reminisces on what his advisor Charney told him when he was a grad student in the 1970s. Some remaining problems in numerical weather prediction. Charney's article from 1967 identifies 5 problems that were described and referred to as certain islands of resistance which seem to hold out stubbornly in the face of all attacks. So unfortunately this still continues, and there are people who write review articles on what will remain. Broadly speaking, the book lists these obstacles from that time. What is the relationship between the turbulent boundary layer and synoptic scale variability? So how do you go from boundary layer processes to synoptic scale variability that we have talked about? How can steep gradients associated with fronts and topographic features be handled in models? So we talked about the Western Ghats, the Himalayan mountains, African highlands, even the let's say traversing of the Madden-Julian oscillations across the maritime continent, and so on, all come up with relations to orography, and obviously they are sharp rising features. When you do models, especially numerical models, how to represent them, how to do the orographic processes, especially rainfalls and so on, accurately still remain issues. Plus the resolution of fronts is also an issue, and there is some evidence that this is not just a question of increasing model resolutions. There are missing process understandings as well which have to be tackled. Do models correctly handle the cascade of energy between scales of motion? We didn't do specific examples, but you can read up a lot of papers on how there is upscale energy transfers under certain conditions in the high frequency or intraseasonal variabilities like MJOs, where you can split it into the low frequency seasonal mean or intraseasonal mean of, let's say, 100 days and longer, and the intraseasonal time scales of 20 to 60 days or so. And then there are higher frequencies which are part of the process, and there is some upscale energy transfer, and of course there are always down scale energy transfers as well. It's not totally clear whether models do them correctly. How are convective processes and large-scale tropical circulations related? So we did this in kinds of related processes. So we talked about the standing patterns like Walker cell, Hadley cell. Then we looked at heatings and the waves they generate and how those waves interact with the basic state, stretching in the zonal direction, meridional shear, vertical shear, and so on. But we never said specifically about the relation or the details of the processes going from convection, which is typically very small scale process, to the large scale circulations. Right, we did a little bit about how tropics are changing and how hemispheric monsoon is affecting circulation changes, Walker cell intensification, Hadley cell intensification, and so on. But that still doesn't connect the convective processes to the large scale. Okay, what determines the structure, variability, and location of such prominent tropical features as the ITCZ? Organization and maintenance. So we have repeatedly seen these pantropical patterns of rainfall. We talked about their movements. We talked about region-specific processes of cross-equatorial pressure gradients, absolute vorticity, zero being zero, and then the processes associated with the inertial instability that are associated with convection, but we didn't go from convection to the moist processes necessarily all the way to the linking processes. So the scale selection is always a very tough issue. Why is there that large-scale evaporation that's feeding these narrow bands of ITCZ rainfall, and how is rainfall organized within that? We talked about Holton's ideas of westward propagating features within the ITCZ, and we looked at some details about eastward propagating features within which you had westward propagating features, super cloud clusters, and those kinds of details. So we know a lot. So the best way is to focus on the fundamental processes that we talked about, and then see how you can extend that knowledge to apply to specific problems that are being listed here as being still open. Of course, from the time of Charney, we have come a long way in terms of data reanalysis, satellites, and many new understandings, but the fundamental open questions still remain. One of the larger scale issue that didn't get fully addressed in the book, we did mention the Indian and Pacific Ocean interaction. For example, we mentioned AMO interaction with the hemispheric monsoon and talked about how AMO is correlated with the monsoon intensity index of vertical wind shear of 850 minus 200 and so on. There are many papers. I picked one. There is another one by Wenju Chai as well, talking about pan-tropical climate interaction. So in the last decade or two, the big thing that has been a focus is how strongly Indian and Atlantic Oceans are able to influence the Pacific Ocean. We had always talked about El Nino as the big monster and its teleconnections to the monsoon and other regions of the world. So you would think Pacific dominates the tropical and extratropical interactions, but it turns out that the Indian and Atlantic Oceans are not passive spectators in this case. They have a strong feedback, and the Atlantic even seems to have a feedback at decadal timescales, as we already implied with the AMO relation to the hemispheric northern hemispheric monsoon system. So the paper puts schematics like this. Again, these are kind of composite pictures, so we have to be careful about what is seen every time and what are kind of composites that evolve when you take multiple events and average them seasonally and so on. So this is just talking about the Pacific with its slow feedback here, the big loop negative going from the winds and sea surface temperatures to the mean thermocline. So we are talking about tropical mean. Remember the recharge discharge oscillation, for example, where you have a strong tilt from east to west, where east is very shallow because of the Ekman divergence and upwelling. West is deep, but during the El Nino, the mean depth decreases with spread of transport outward, and the positive anomaly in the east and negative anomaly in the west, and so on. So there are these slow time scale feedbacks. There is fast feedbacks between SST and winds, and then the Pacific convection, which gets perturbed during an El Nino, affects winds over the Indian Ocean, which has quick feedbacks to the SST, which then has a slow feedback to the winds over the Pacific, but also there is noise added in the middle in terms of these westerly wind bursts, MJOs, and other features that what we refer to as multiplicative noise. For example, when the West Pacific convection moves, the westerly wind bursts can keep moving with them and get larger in fetch and strength and duration. Okay, there is a similar interaction on the Atlantic side with a feedback between the Atlantic and the Indian Ocean as well. So this can be looked at in terms of the mean state we have talked about, with the warm pools in each ocean, the Indo-Pacific warm pool being the giant with this large convection here, associated Walker cells, and of course there is the meridional cell. On El Nino timescales, one can look at seasonally stratified links between the evolution of El Nino and the Indian and Atlantic Oceans. I won't go into the details here. You can read up the paper. I just wanted to close the chapter by mentioning that there are very strong feedbacks between each tropical oceans, and there are fundamental questions associated with them as to what is there a forcing that is kind of unifying the response between the three basins. For example, such a monstrous heat source here can be seen as a potential contender for perturbing the entire tropics, and then internal dynamics generating these feedbacks. Okay, so during the June, July, August of the ENSO evolution, obviously there is shift of the convection towards the east. There is anomalous warming, but this happens only for very strong El Niños. For weaker El Niños, the summer signal of the El Niño year is not that strong, and hence the links to monsoon are also not that strong. Plus, where the heating is located can make a bigger difference as well. For example, if the El Niño is focused on dateline warming, there is some evidence that the monsoon teleconnection is stronger. But the Indian Ocean has a dipole-like anomaly here, with surface wind anomalies being easterly. The Atlantic also has equatorial and off-equatorial wind signals, and those evolve over seasons. As you can see, September, October, November, when the IOD peaks, has a clear east-west pattern here. So there is El Nino-like character, which is opposite, or you can think of the Indo-Pacific tripole that we talked about. But you can begin to see wind anomalies evolving here, which by DJF have changed, and there are surface pressure anomalies associated with these as well, with the Northwest Pacific anticyclone evolving into a high pressure system, which and there is the extratropical link from the ENSO into the Atlantic through this so-called Pacific North American pattern, which is a wave train that is going off into the high latitudes and coming down into the Atlantic, whereas these are direct tropical links affecting the northern tropical Atlantic, which then relates to the tripole pattern of the North Atlantic oscillation we had seen. But by DJF, you can see the Indian Ocean has warmed over the whole basin, which persists into the next season. So MAM, after the El Nino has peaked, is warm, which is able to create anomalies here as well as through the Philippine anticyclone, and drive the transition to the next phase of ENSO, which is typically a La Nina. Again, not every El Nino is followed by a La Nina, and that has to be kept in mind. So these are composite pictures, but at least this gives you a sense that there is a strong relation between the tropical oceans, and this is the same thing with the Atlantic feedback to the tropical Pacific, which I won't go into, but there is a seasonality there as well, which goes directly through the Walker cell and then propagates into the north through the Hadley cell. But on decadal time scales, now it's fairly obvious that the Atlantic has a fairly strong influence on the Pacific Ocean through this Atlantic multi-decadal oscillation, which we briefly mentioned in the last chapter. So the decadal interbasin connections are also turning out to be important. The Indo-Pacific basin connection is implied through this Gill type response. If you have warming here, Gill response is basically a kind of a linear wave response given the diabatic heating in the atmosphere. So you can see there is convergence, and then there is Kelvin wave ahead, Rossby wave behind, which is the direct surface expression and upper tropospheric expression, and so on. And then there is the Atlantic Pacific basin connection as well through the Gill type response. You can see here on both sides. So there is convergence on this side and from this side as well. And then the Indian Ocean is argued to be able to amplify the Atlantic-Pacific Basin connection, which gives you a different type of response compared to just the Atlantic influence on the Pacific Basin. I'm kind of running through them because these are arguments which are based on evidences that are building up, but each one is some sort of a consistency check based on data and the correlations. Mechanisms are not always that easy to come by, especially because they are not consistent. For example, AMO is a very low frequency mode, multi-decadal mode, and I already mentioned that the mechanism for this mode and the selection of this large scale and whether ocean plays a role in it and so on remain open. The same thing for Indian Ocean dipole. Even though it's such a solid mode that's very obvious, when it's very strong, it's obviously coupled ocean atmosphere. But there are many times when the fluxes can create the east-west mode as well. And the role of the Pacific and specifically El Nino or the maritime continent rainfall anomalies on the IOD remain quite open. So same for Atlantic zonal mode or the Atlantic Nino. It seems related to the Atlantic ITCZ, so there is a coupling between the meridional mode in the Atlantic and the Atlantic Nino through the ITCZ. There are some nice papers there as well. But the Atlantic is also strongly connected from the tropics to the higher latitudes through this tripole mode in SST that we talked about. That's kind of indicative of the North Atlantic oscillation. And then you have the Atlantic multi-decadal oscillation on top. And then the North Atlantic oscillation itself is related to something else that's called often as the Arctic oscillation, which relates to the higher latitudes. So all these questions remain. That's why I'm kind of just exposing you to these ideas and not so much trying to explain the mechanisms, because even though there are a lot of papers, there are a lot of open questions. Okay, so I will leave there with that. This is a slightly longish podcast compared to the others, but since I didn't want to stretch it unnecessarily, I just put it all together in one. So again, focus on the fundamentals that we learned about in terms of tropical dynamics of the atmosphere and the oceans, and think about these remaining questions, especially the pantropical interactions, which are working through those basic modes of standing Walker cell, Hadley cell modes, and the waves and wave mean flow interactions between them with the tropical extratropical interactions. Does that simplify life? Yes, if you know the fundamentals, you can probably find a way to take the reductionist approach of extracting one problem and solving it and then putting it back into the more complicated system. That approach may or may not work, but that's the best we can do on most occasions to simplify resolution of particular aspects of the bigger full Earth system problem, because we haven't talked much about the land interactions at all. The vegetation feedbacks, the capacitor effects of the Indian Ocean or vegetation, and so on and so forth. So that's still not something we talked about because we're focused on the atmosphere and the ocean. Land is a big part of this, especially in the monsoon dynamics, right? So let's leave it there, and I hope the course came together well and serves its purpose. And if you have comments, you know how to send me emails, right? Good luck.